All right, we're going to start by going over one of the problems in the yellow packet. That is the Phyzjob series problem number 1. So it shows you an example above. The equations that you need are listed in red. So the new equations are these power equations, a few different variations, which we'll get to in a second. Also, you'll notice that this little cursive E symbol stands for EMF, which also means EMF equals electromotive force, which is also equal to voltage. So you'll notice it's measured in volts, so kind of means the same thing there. So in this case, from the battery, we're getting 10 volts. So we have a series circuit. It's going to be helpful to use your foldable for this one. First, we're looking at the equivalent resistance. So another new term, equivalent, here. This is the same as total resistance. In a series circuit, we add all of the resistors together. So here we have resistor 1 is 12 ohms, and we have resistor 2 is 3 ohms of resistance. Remember, the current runs from positive terminal to negative terminal. So the current's first going to go through this resistor, and then what's left of that voltage and current will go through the resistor 2. So for our total resistance, we can do a pretty basic equation, which would just be 12. It'll take me too long to find the ohm symbol. I'll spell this out. 12 ohms plus 3 ohms equals 15 ohms. Done. That's our total resistance in this series circuit. For part B, the total current. Total current, we're going to need to use the total resistance, so 15 ohms. We're going to use the total voltage, which in this case is 10 volts, and we're going to use Ohm's law to find the total current. So if we add part B here, B, I total equals V total over R total, or R equivalent. Let's move this down. Okay. So we would plug in our, I total equals 10 volts over 15 ohms using our previous answer. If we divide 10 by 15, we should get 0.67. Our units of current are amps. So I total should be equal to 0.67 amps, or 2/3 amps. You can also check your answer down here. The answers are mirrored, so you can check these backwards. Part A, 15 ohms, correct. 0.67 amps for part B. Let's move on to part C, where we're using our new equations. So for part C, we're choosing one of these variations of power to calculate the power dissipated or used by resistor 1. So in this case, we know the total current flowing through from part B. We also know the resistance, which is 12 ohms, just of this resistor. So if we know current and resistance, we can use this last equation, P equals I squared times R, to solve for total power. So let's go back here. Part C, power equals I squared R. That will equal 0.67. This little caret means squared, times 12 ohms. Again, we're using just the resistance of resistor 1, not the total resistance of the circuit. That should give us, answer to part C, should give us 5.4 watts for power. Let me just verify on my calculator. That is the answer that's on the key. Okay, so 0.67 times 0.67 times 12 equals 5.4, rounding to the 10th. Last part, we're almost there, voltage across resistor 2. This is not the same as the total voltage. This comes back to the voltage loop rule. The voltage gain from the battery or the voltage source has to equal the total voltage drop. So notice I have voltage drop 1 equals on top here, and voltage drop 2 equals. So because we don't know the voltage drop of resistor 1 right away, we're going to use a mini Ohm's law equation for resistor 2. So down here we have V drop of 2, so voltage drop over resistor 2, equals the total current, current is the same in all series circuits, times the resistance of resistor 2. So we would plug in 0.67 amps times 3 ohms. And that should give us 2.0 or 2.01 volts. So what that would mean is the voltage would have to drop 8 volts over resistor 1. So up here I can fill in 8 volts, and here I would have 2 volts. Reason being, 8 plus 2 has to equal 10, or the total voltage drop across the series circuit. Okay, you can comment below with any questions. I hope this helps.